Good afternoon, good morning, good evening. Thank you for joining us here for this webinar on heterogeneous multiprocessing using Zephyr and Linux and the i.MX 95. My name is Drew Mosley. I am with Toradex, and I am here with my colleague Mohammed, who will be presenting the bulk of this material. He is a software consultant with Mab Labs, and we work together on a number of things, so I can assert that you're in good hands with Mohammed. A couple of administrative things. If you having any technical issues, please use the chat. We do have folks monitoring that to get you unstuck if you're having technical issues with the webinar itself. We will be doing a Q&A at the end, so if you have questions, feel free to pop them in the questions tab at any time, and we'll take a look at those at the end. Just a brief agenda. I'm going to start off by just kind of introducing Toradex in case you're not familiar with us or our products, and talk about specifically a couple of our newest exciting products. And then I'll hand over to Mohammed, who will be going through the details of heterogeneous multiprocessing, what it is, why you would want to do it, and then some of the technologies involved in implementing this, and then dig into the specifics of Zephyr, and then show how it all works together with with an actual demo of some Zephyr apps running on Toradex hardware. So if you're not familiar with us, I'd be kind of surprised since you're at our webinar, but maybe you stumbled across this and are just coming up to speed. At Toradex, our tagline is "We make embedded computing easy." We make a range of system on module boards, as well as single board computers, as well as even custom product solutions for folks that are developing higher end embedded devices running Linux, in industrial, automotive, medical spaces, that kind of thing. We have the entire Horizon system, which is our Linux system that runs on the device, as well as all the software development tools and the cloud services for over-the-air updates, remote access device fleet monitoring, that kind of thing. Obviously, the over-the-air updates is very important now with the EU Cybersecurity Act that has come out. Being able to update the devices in the field and keep an eye on CVEs and things like that are a very important part of that regulation and the compliance with it. So a couple of our exciting new products are based on the Smart Standard. We have one based on the i.MX 8M+, and another one based on the i.MX 95. And the software system that we have, Horizon, is fully compatible across those new platforms. They are in the process of being brought up and released today. If you do have a need for that, feel free to reach out. So looking a little bit more in depth here at the i.MX 8M+, you see here that it's 2.2 smart compliant. It does have the quad core A53s, as well as the NPU, the Cortex M7, and a lot of other very interesting features that works for fairly high performance workloads. And then if you need even more than that, we have the i.MX 95 based smart module. You see it has six Cortex A55 cores, the M7 core, the M33 core. Mohammed will go into some of the details of the various sub components of that module. And then the specific board that we're using for today's webinar is the i.MX 95 Verdin EVK. This is the evaluation kit that we designed in collaboration with NXP. And this is available from NXP, but it is designed and supported by Toradex. And with that, I think I will hand over to Mohammed for getting into the meat of the content.
Thanks, Drew. So what I like to do before, at the beginning of every presentation, is understanding the motivation behind it and what the point and purpose of the presentation is in the webinar and the talk that I give. So if you're familiar or if you're experienced with traditional embedded software development, usually if you have a system, it most of the time has one particular CPU type, but there are instances where there may be two cores or CPUs that communicate with one another. So typically, Linux-based applications are really meant for the ARM 8-core CPU. It's usually beefier, more powerful, and it has a lot more features. And so it can support Linux along with multiple processes and multiple applications that are doing different things as part of your overall product. And then you have the ARM M or R core CPUs, and they're really meant for RTOS or bare metal applications that have more real-time constraints, and they're not really as power hungry. They're generally lower power than the A cores. So each sort of CPU has its own disadvantages and advantages that make it perfect depending on the application that you want to target. And if, let's say, you have a particular system that requires these multiple paradigms where, let's say, there's a Linux component and there's an RTOS or bare metal component, then you really need to have multiple CPUs that have these different types of cores, right? And then typically, because they're different pieces of silicon, different chips that are running on your system, you need some mechanism or bus to communicate between the two processors. Usually, I've worked on projects where we use UART, I2C, and SPI as really the main form of communication between the two. And typically with these systems, these sorts of multi-core or multi-CPU systems have really two different software paradigms, right? So Linux is running on the ARM 8 core, and typically that's where the GUI is. There isn't any necessarily real-time operation that's happening there. It's more for user interaction and user feedback, right? So a user clicks a button, some information, some control information is sent down to the ARM M core, and then it periodically status or feedback is provided from the ARM M core back to the GUI. So the GUI isn't really doing, so the ARM 8 core isn't doing anything necessarily real time or mission critical. The ARM M core is where a lot of the meat of the application that's critical and that has real time requirements is implemented. And so in medical and automotive robotics and functional safety applications, where we see a lot of these paradigms where one particular processor, usually an ARM M or R core, is running the real-time component of the overall system, and the A core running Linux is mainly responsible for the GUI and user interaction. So if we have, let's say, multiple CPUs running on different chips, right, on different silicons, the issue that offers is that, or that results in, is we increase the complexity of the design, right? So we have additional hardware, right? Not only just in the chips, but also in the communication. There's additional layout that needs to be done, and it needs to be managed. The buses need to be, if we have high-speed buses going between the two processors, then those need to be carefully designed and routed and layout, et cetera. And also from a mechanical point of view, right? We have to consider that there are two different chips. They may have different thermal properties, right? That they may need different thermal adhesives. That the enclosure may affect the design as well. So because of, and of course, like the firmware software is always going to be, we have to have two pieces of firmware and software. But in the case of multiple distinct processors that are in our system, we also have hardware, electrical hardware, and mechanical considerations. Right, and then this can result in increased development and debugging, again, because you have multiple components, which inherently results in additional time and cost, and then that can result in a fair bit of frustration because, again, we have to deal with potentially hardware, mechanical issues that may drive firmware software, and they may in themselves be intertwined. So one thing that we could do potentially is, instead of having distinct processors on different chips communicating over different sorts of buses, we can place the processors on the same piece of silicon, right? So what we could do is we can take the ARM core and the ARM A core and essentially just put them on the same processor and use shared memory to communicate between the two cores themselves, instead of using an explicit communications bus. And so what this does is it eliminates essentially the electrical and mechanical elements that we need to consider because of the two processors that we're going to use, right? So it reduces development and debugging, which inherently reduces time and cost, and reduces frustration, and it leads us to a much quicker or cheaper, much cheaper and much time, reducing time and cost in developing our final product, right? And also this is the frustration. So what ends up happening is because we eliminated, for the most part, the electrical and mechanical challenges of having two distinct processors, our challenges mostly devolve into strictly firmware software, right? We had that previously, but now because this is the only element that we have to consider, it reduces a fair bit of the work that we have going forward as in our team as a whole. So just a quick kind of poll that we're going to take. What sort of HMP projects have you developed, or are you developing? Are you interested in? Are you just curious? Are you working on a medical device? Are you working in automotive or robotics? So we'll give people a few seconds to chime in with their responses and then proceed from there. All right, so let's see how everybody responded. So a little over a third of everybody said that they're just curious, that they aren't necessarily developing an HMP project. Then in second place, we have automotive, which is great. And then we have a close third is medical devices, and after that's robotics, right? And so, a bunch of you are just curious, which is great. We'll see what sorts of technologies and applications HMP can enable and understand the nitty-gritty details. And for those that are actually using it in a project, you'll get some understanding and familiarity with how to leverage HMP in your project with Zephyr and Linux. So now let's get into the details of HMP, how the technology works, right? So this framework or this concept was originally added to the Linux kernel by Texas Instruments. And if you're familiar with Texas Instruments, they have their bread and butter originally was DSPs and real-time microcontrollers. And then eventually they migrated to having SoCs with DSPs and microcontrollers, as well as Linux-capable cores. And so they needed a mechanism to be able to control their lower power real-time controllers and chipsets, controllers from their higher application core processors, right? And so they developed and mainlined what's known as Remoteproc and RPMsg to the Linux kernel. And so what that allowed them to do is essentially let Linux manage the lifecycle of the remote processor and the software running on that remote processor. And also it allowed the Linux side to communicate with the firmware that was running on the remote processor. And in the case of Texas Instruments, back in the day, they had an RTOS and it was called SysBIOS. Nowadays, I think it goes by a different name, but essentially they needed some sort of implementation that allowed the Linux side to be able to communicate with their SysBIOS implementation that was running on their remote DSP or remote MCU. And so that's the genesis of kind of what we're going to talk about, a little bit of history. And then what ended up happening is there's an organization called OpenAmp, which stands for Open Asymmetric Multiprocessing. And they built off of, it was a project that built off of TI's work. And the motivation there is to take what TI had developed and standardize a lot of the communication. Again, TI developed it for their specific use case, for their specific hardware, and even their particular RTOS, right? And what the OpenAmp project did is standardize it and generalize it so that any sort of microcontroller, any sort of bare metal or RTOS implementation can communicate between the Linux OS, and Linux can manage all of these processors and the firmware that's running on these microcontrollers and processors. And they extended it. They provided a reference implementation. They also have a Yocto layer that they also maintain. And so you can have a complete standardized and generalized implementation of the Remoteproc and RPMsg under the OpenAmp project umbrella. And just real quick, the distinction between Remoteproc and RPMsg. So Remoteproc, we'll go into more detail in the next slide, but it's mainly for lifecycle management, and RPMsg is mainly for interprocessor communication to send messages essentially back and forth between the different processors on the system. So let's take a little detour and see how HMP can be enabled on the i.MX 95. So the Toradex Verdin i.MX 95 has 3 cores on the same piece of silicon. We have the A55, which runs our Linux OS. And it's not necessarily meant for real-time operation. Of course, as most of you are probably aware, the real-time patches were mainlined recently into the Linux kernel, so there is some real-time capabilities, but in general, the A cores are not really meant for what we traditionally known as real-time operation. Then we have the Cortex M33, and it has a specific purpose on the i.MX 95. It runs what's known as System Manager, which is responsible for booting, let's say, the M7 before the besides the A55. So the A55, as we're going to see, can manage booting and loading of the M7, but the M33 can also do that. And if you, let's say, need to load the M7 and run it before Linux starts, you can do that through the M33 in the System Manager. And the cool thing about this is actually System Manager code base is actually open source. So if you need to make customizations and modifications to, let's say, allow you to boot particular firmware or to control the boot processes of the M7, you can do that because source code is available to you. And then finally, the interesting part of this particular webinar is the Cortex M7, which runs the real-time or bare metal or RTOS firmware that can be controlled by both the M33 and the A55. So just going back into what the Remoteproc and RPMsg constructs are responsible for and how they're different and similar. So Remoteproc is responsible for loading the firmware onto the remote processor. So this is something in Linux from the point of view of the firmware that's running on the MCU. There isn't really any construct or awareness of Remoteproc. It's really just a mechanism in Linux to communicate and to load firmware on the remote processor and then start and stop it. RPMsg is where a lot of the interesting things happen on the MCU side. So there you need a framework to be able to allow communication between the Linux and remote MCU. And so that's where RPMsg comes in. So if you want to support RPMsg on the MCU side, you need that framework built into your code base. Okay. So now let's understand what the Zephyr project is. So it's gained popularity significantly over the past few years. And one thing that I like to think about Zephyr is that it's not just an RTOS in the traditional sense, it's an entire ecosystem. So not only does it include typical RTOS kind of kernel primitives and corresponding data structures such as threading and tasking, semaphores and mutex and message queues, but it also includes other software stacks. And the cool thing about Zephyr being an ecosystem is that these software stacks are maintained, right? So somebody, it's an open source project, it's pretty extensive. You have maintainers that are part of that have pretty impressive resumes. They're part of large organizations like Analog Devices, STMicro, NXP, right? And so they're all vetting, and Nordic, and they're all vetting the software that's running, that's pulled into the Zephyr ecosystem, right? So you can rest assured that what the software stacks that you're using, the source code that you're using, has gone through a rigorous review process, and so you don't have to worry about if you've done traditional RTOS development before. Usually, what would happen is you develop your application, and then either you need to rely on the vendor IDE to have a particular software stack that you want to use, or drivers, right? Or you need to scour the internet for some random piece of code or develop your own, right? So there's some variability and question whether the software stack is valid or not. And you have to, and there's some time required for you to make sure that it's correct, right? Whereas with Zephyr, you can have some degree of confidence that the source code that you're using has been reviewed by somebody and has gone through a certain degree of rigorous testing so that you can use it on your own application. And Zephyr is still growing, right? It has support for more than 500 boards, and this continues to grow. So just another poll for everybody that's out there. What is your level of expertise and comfort in using Zephyr? You've never heard of it, you've tried it once, you regularly use it to develop applications, and if you're an expert, you've submitted PRs, you've written your own device drivers, and they've been accepted into the Zephyr project. So give everybody a few seconds to answer these questions. All right, let's see how everybody did. So Yeah, this is great. So close to 3/4 or 2/3, 68% of everybody has tried it once, and then 26%, a little over a quarter, and have never tried it. 5%, which is impressive, of you have PR submitted, which is great. You have some expert level of using Zephyr, and then 0% don't regularly use it. So I hope to convince those that haven't regularly used it to develop applications using Zephyr. I hope you'll reconsider that going forward. All right. So this is just a quick overview of the extensive kind of software stack in Zephyr. So from at the top here, this is the application that we write as application developers, and you can see it's really minimal compared to the rest of the software stack. And all of this is provided by Zephyr for us, right? We can see that we have protocols, right, for communicating for IoT devices. We have security, right? We have layered communications, TCP, UDP, right? And then we have the actual core RTOS kernel itself. And then also not shown here is the drivers themselves as well. And then, this is right here where it's device management. And also we have the low-level API. So we can see that you get a lot of source code that comes along with the Zephyr ecosystem, and it's not, you don't have to do, like, your responsibility is essentially just creating the application itself. So one of the cool features about Zephyr, again, going back to that it's an ecosystem, is what's known as WEST, and it's a meta tool. And what that means is it's essentially just a layer that hides the underlying tools that you need to use in your day-to-day process and workflow as an embedded software engineer. So you don't need to worry about what the underlying tools are, what the underlying build system is, what the underlying kind of mechanism to flash it. All you really care about is I need to just interface with WEST, and it'll handle everything from setting up your project to compilation to debugging and flashing itself, and even to run tests, right? You don't need to worry about, oh, what's the underlying infrastructure that's used to run tests. All you need to know is how to write the test, and then you can just use WEST to execute the test that you need. And the other cool thing about Zephyr is that it's really easy to get started. It has numerous sample applications that we can immediately compile and load. And even for this webinar, we're just going to be using the out-of-the-box samples that Zephyr provides to see the OpenAmp infrastructure in action. So you really don't need any development to get started. All you need is a hardware. You need to just set up your environment, and you're ready to go. And just taking a little bit step further, a little bit more intermediate topic is Zephyr has a really structured and organized way on how boards and SoCs that live on those boards are implemented. We're going to see kind of examples of that later on. And one thing, if I were to ask anybody to remember, kind of associated with Zephyr, is three things, right? It's source code, right? We're all familiar with source code. That's embedded software, right? Device tree, right? If you have a Linux background, you kind of know what device tree is, but we'll go into a little bit more detail there. And then finally, it's kconfig, right? So these three things kind of make the crux of Zephyr, right? And so if you take away anything from this webinar, I hope you take these three things away. And if you need more information on more examples, more blog posts, webinars that I've done in the past, feel free to reach out to me, and I can point you to resources on how to better understand these sorts of constructs in Zephyr. So let's kind of look at an example of basically this sort of paradigm where we have source, device tree, which is what DTS means here, and kconfig, right? So if we look at where the boards where the board implementations are located in Zephyr, they're all under the boards directory, and then they're grouped by a particular vendor. So in this case, we have NXP, and then in NXP, we have the directory corresponding to our 95 EVK, right? And we can see, again, the three components here. We have a .c file that performs some initialization of the board itself. We have our device tree, which specifies what hardware is present and details about the hardware that's present on our EVK. And then we have the kconfig, which enables certain features associated with the hardware. And so if we look at basically the kconfig that I just pointed to, we can see here that all this is doing is it's selecting the M7 CPU that's on our SoC if we've told West and Zephyr that we want to build for the M7. So this has another set of cascading effects that we can see here. So here we saw the boards that are present, and now here we see how the SoC itself is present in Zephyr, right? So if you can imagine, we have our board here, right? And then we have our SoC here, right? And then in the SoC, we have essentially the M7 here. So essentially, we're kind of drilling down to define this individual hardware components, right? So here we have where the SoC is located. It's again, same structure as the board files, right? We have a vendor, we have a particular class of SoCs, and then we have another subgroup of the SoC as well. So we have the i.MX 9, right? And then here we have the directory for the 97. And again, we see the same structure here. We have a kconfig that specifies what sorts of features and configuration options for the M7. And here we don't have a device tree, but instead we just have the actual C code that is responsible for bringing up the M7 and configuring initial set of peripherals. And then if we look at basically the kconfig right here, we can see that this is the link between the device tree and the kconfig and then eventually the source code. So if you have any sort of background in Linux, the device tree is managed at runtime, right? Linux looks through the kernel looks through the device tree. It identifies what devices need to be enabled, and it goes through the process of loading or calling the appropriate functions to initialize the hardware that the device tree has told it about. That's not the case with Zephyr. Everything happens at compile time. So what ends up happening is the Zephyr build process, it converts the device tree into a header file, and then there's what are called bindings that convert the device tree into things that can be referenced in source code. And so we can see part of that binding here, where in the kconfig actually it specifies, okay, which node we're going to use in the device tree that corresponds to the flash system, and then eventually that's used by the software to do the appropriate initialization. So that's really briefly how the three kind of come together, right? So if you have more questions, we can try to answer them later on, but if you want more detailed resources, feel free to reach out to me and I can point you to kind of resources that I've worked on, blog posts and webinars that can help you kind of navigate this in more detail. So now let's actually go through the process of seeing a remote proc demo, right? So first we want to do is with any kind of Zephyr project is retrieve the source code, right? So again, we use West for everything. So the first thing we want to do is set up our project, right? So here I have a fork of the Zephyr repo, which is what I usually do for driver development. And for most of my webinars, because sometimes what ends up happening is I need to make a change to Zephyr, and then I can have it committed in my own fork, and then what I end up doing is usually mainlining it. And so, this is publicly available. You can also do the same, and you just run this command to get things set up, and then you do a West update. And what West does is it looks for a west.yaml file in here, and that YAML file describes all of the source code, right? That's internal, right, as part of Zephyr, and also external, right? And it fetches all of that source code that you need to actually build any sort of firmware that you want to run with Zephyr. Okay, and now we're going to see an example of actually how to build a Zephyr kind of hello world example. And in this case, we don't really need to worry about remote proc because, again, like I said earlier, remote proc is strictly a Linux, a construct in Linux. The MCU firmware doesn't really care. All it cares is that, oh, something is loading firmware into the M7, and it's telling me when to start. It's just telling the M7. So the firmware really doesn't care doesn't really care about remote proc. So let's take a quick look at this demo. Okay, so here we can see basically, like I said, right? So we have a bootloader that's also part of the Zephyr ecosystem, right? But again, this is not part of Zephyr proper. This is a bootloader. MCU boot is the preferred bootloader, and the source code is contained in this bootloader directory. Modules has a ton of different software stacks that are present. It has crypto, embed TLS. It has drivers that are specific to vendors like NXP and Nordic, right? And so all of this, all of the source code under modules don't conform to the Zephyr API. And so what you eventually need is a thin layer, right, within the Zephyr directory that is essentially interfacing to the source code in modules that our applications can use. And then tools are extraneous tools that we might want to use alongside our alongside the compilation and development process. So now that we understand kind of the different directories, we can go ahead and build our example. And so this, so what this command does is west build, and then -p just tells us to do a pristine build, a clean build, and then -b specifies the board that we want to target. So in this case, it follows that square kind of architecture that I was kind of mentioning here, where we have, right. So what it has here is you have the board, right? And then you have the SoC on the board, and then you have the actual CPU that's on the SoC that you want to target. And then finally, we want to build, so like I said, Zephyr has a lot of samples, right, for different drivers, different subsystems, and we just want to build the hello world sample here, right? So we're just going to see that in action. And we can see here on this line where it says it found the board DTS. So again, it found our device tree that corresponds to the 95 EVK, the SoC that's on it, and then the M7. And then what ends up happening is Zephyr or West takes different overlays. We're going to see what an overlay is later, and it converts it into a final DTS file. And then eventually, like I said, everything happens at compile time. So the device tree is converted into a header file, which then the source code uses to reference the device tree. And then we can see the build process. Okay, and so now if we look at the build directory, it's under build Zephyr. And then if we just see all the corresponding outputs in Zephyr, we can see we have the .bin, which is just just raw bytes that correspond to the application that we're running. The device tree, right? We have the final device tree. We have a device tree that was generated before any sort of customizations happened to it. We have the ELF file that contains a lot more information than the bin file, the mat file that we can use for debugging purposes, etc. So there's a fair bit of information that we can glean from that helps with debugging with all the build artifacts that West produces. Okay, so now we're going to see how can we actually run the Hello World application that we compiled for Zephyr. How can we run it from the Linux side on the i.MX 95, on the Verdin i.MX 95? So first thing we're going to do is transfer it, the ELF file to Linux that's running on the i.MX 95. So it's on 10.10.2.22 on my network. And then we're going to SSH into the Verdin. So on the bottom is the SSH window for the i.MX 95 on the Linux side. And then on the top is the terminal console interface to the M7 that's also present on the i.MX 95, right? So we transferred over this file. So we're going to navigate to the sysfs entry that corresponds to the Remoteproc driver, right? So we go to the sysfs location. We're going to tell Remoteproc that we wanted to load this Zephyr.elf file by just piping the path, by sending the path to it to the firmware sysfs entry. And then all we're going to do is we're going to tell Remoteproc to start the firmware. And we can see that on the top, we can see that the hello world is output. And then we can also see the board, the SoC, and the CPU on the SoC that was generated. Okay. And we can, if we look at the state of the M7, we can learn about the state of the M7 by catting the state sysfs entry, and we can see that it's running. So now let's talk about RPMsg. So we looked through Remoteproc, and now we can look at RPMsg. So again, samples are available in Zephyr itself, right? So in the case of RPMsg, it's under samples, subsys, IPC. So again, Zephyr has a lot of samples for a ton of different subsystems that are present, and we can, again, we don't need to do any coding. We can immediately just use these examples to just try out a particular feature. In here, there are a bunch of different examples that correspond to different interprocess communications paradigms and frameworks. So in this particular instance, we're going to look at the OpenAmp RC table example. And here, the structure of it says that the prj.conf has configuration options that correspond to the application. And then the boards directory is interesting because it contains specific configuration you can consider them to be overrides from the defaults, right? So again, going back to the three pillars of Zephyr is kconfig, right? So we have the config, right? And then again, in here for the device tree, we have what's an overlay. So the overlay, what it takes is, what it's responsible for, it's responsible for overriding the default entries, the entries in the default DTSI file for a particular board, SoC, and CPU type. And then of course we have the source. So we have, kconfig, and then also the conf here is responsible for enabling or disabling certain features that correspond to the hardware that we want to use away from the default, right? That's something we need specifically for this particular application. Okay, so now let's take a look at the configuration file under the OpenAmp RC table example under the boards directory, right? So what this is doing, it's enabling, so this is much smaller. If you actually dig into the kconfig for the SoC, it's a lot more verbose on this because it specifies everything that we want to enable or disable by default. And this is only really specific to this application, right? So, for example, we can see that there's a couple of entries, because if you're not using, let's say, OpenAmp on, let's say, the M7, right? If you just want to build Hello World, there's no reason to turn on, let's say, OpenAmp, right? Because you're just going to be compiling things and make the size of your binary a lot bigger than you need it to be. So in this case, by default, it's disabled, but we're enabling it because we need to. And for example, we need like this mbox that we're going to see in a little bit, and we need that for it. And then also we need this OpenAmp copy RC table entry. And so we've turned on these specific features that we need for this particular application, and we can see that in the conf file. And then if we look at the other kind of pillar, right, we can see the overlay file, right, that corresponds to the device tree. And so usually when you're doing any sort of interprocess communication using OpenAmp in Zephyr, you need three main components defined in your device tree. You need the IPC shared mem, that's what this stands for. You need the RC table, we'll go into what these are in a little bit. And then also the mailbox. And then again, like I said, we'll talk about what these are and why they're important in the context of RPMsg and OpenAmp. And so these, these, if you look at these, you notice these ampersands, and if you have any background in C, right, ampersand usually means a reference, and this is no different, right? This again is taken from the Linux kind of device tree implementation, and these point to nodes, other nodes, right? So eventually what happens is the source code looks for what this node refers to, and it sees that, oh, this is referencing this node in the device tree, and it gets the necessary information from that particular node in the device tree. And in the same overlay, actually, a lot of these are defined in the overlay itself. So here we have a shared mem node in our device tree overlay, and essentially this informs Zephyr which driver is responsible for implementing this particular device. And the same thing in here, right? So essentially, these two nodes from a strictly software or C point of view are essentially the same. The only thing that's different is that the addresses on where this memory is located and how big it is different, right? And so we can determine where the location of these by two mechanisms. One is using our reference manual, right? So if we look at the M7 portion, it's a little bit tiny here, but if you look at the M7 portion of the i.MX 95 reference manual, you can see that this region points to the DRAM from the perspective of the M7. So now the DRAM actually begins at 800 hex 800,000 or 8 million. But we notice that these entries actually point to regions within that. And so the way we would determine that is by looking at the corresponding device tree on the Linux side, right? Because again, we'll see why it's important for us to get these locations correct. It's important because this is how the Linux and the M7 side used to communicate between one another. And then also we have this mailbox, and we'll see why that's important. But this mailbox refers to this MU7 entry in the device tree. And if we see where that's located, that's actually located in the M7 DTSI file. And this defines the details of this particular mailbox, right? And if you look at, again, the reference manual for the and look at the M7 section, you'll see that the mailbox, this particular mailbox, is located at this address space. And then we can see here the default is that it's disabled. So we also need to enable this particular mailbox in our overlay device tree. So just to take a step back, we saw kind of like these three different components. We saw the shared memory here, right? We saw the resource table here, and we saw this mailbox. So why is that important? So shared memory is obvious, right? You need some piece of memory for the cores between the A core and the M core to be able to communicate between one another. So you need some piece of memory to be able to share data, right? The resource table is important because it tells the Linux side what state of the processor or what peripherals the processor needs to have enabled before it can be turned on, right? And so the Linux side interrogates this resource table in the L file to determine the capabilities of the remote firmware. So for example, if let's say we want to use a TTY interface, then that resource table tells the A core, hey, I have a TTY capability, you can use that. And so that basically triggers, and we're going to see this later, that triggers essentially drivers on the Linux side to be loaded to serve that capability on the Linux side. And then finally, we have the mailbox, right? So we need some sort of interrupt or signaling mechanism between the Linux and the firmware side on the M7 to tell both sides that there's information in the shared memory that has been placed that is ready for you to process, right? So again, we need shared memory, obviously, we need this resource table more for capabilities, and then we need a mailbox for signaling and interrupt. So now let's take a quick look at how to actually build the Zephyr demo in, build the RPMsg demo in Zephyr for the i.MX 95, Verdin i.MX 95. So we can see here, like I showed earlier, we're in sample subsys IPC. And then in here, again, we go into the OpenRC table, right? And again, we're going to do the same build command, right? Or similar build command as a hello world. We're going to define the board, the SoC, and the CPU that we want to target. And then we specify the directory that contains our application, right? And we can see the same process happening again. And we're just going to transfer this file over. Okay, and that's it. So again, the process for building the hello world, the process for building the RPMsg demo is no different from the hello world, right? The details are hidden in the kconfig and the overlay, and of course the source code, right? That allows us to manage the interface and communication between the Linux side and the M7 side. So now let's see how to run the demo. In this case, I apologize for the confusion, but the Linux side, the SSH terminal is actually on the top, and the console to the M7 is actually on the bottom. So we're going to see, again, same process as before. We're going to load we're going to navigate to the sysfs entry that corresponds to the Remoteproc framework. We're going to tell it which ELF file to load. It loads it, and then we're going to start it by echoing start to the state. And we can see that on the bottom side, we can see that, oh, we're getting a bunch of messages and notifications from the Linux side, right? That, hey, there's message there, and this is the content. This is where we got the message from MB1, and here is the message that we received, right? And then if we look at the, if we look at the dmessage output on the Linux side, right, we can see that at the bottom, right, we can see that we're getting responses back from the M7, right? We get a message back. Essentially, what we're doing is we're on the M7 side, we're essentially it's just an echo. So the Linux side sends a message down to the M7, and then the M7 just echoes it back, and we can see that. And then at the end, we can see that once the Linux side has determined that the M7 has essentially run to completion, it actually tears down the rest of the drivers that it needs on the Linux side, right? Because there's no point in maintaining those essentially, right? And then we can see at the top, we can see some kernel output telling us that, oh, it's launched essentially the i.MX RPMsg driver, right? It's going through the initialization sequence there. We can see that it's loading the ELF file as part of the image, and then it's booting it, and then it's going through the process of bringing up the Remoteproc and RPMsg infrastructure, right? It's going through the initialization sequence, and then the sample driver is basically just going through the ping pong echo example, right? Yeah, and so that's just the demo in a nutshell. It isn't too complicated, but I think it kind of demonstrates some of the power behind the Verdin i.MX 95, right? We saw how, just to summarize, we learned about the advantages of having different types of cores on the same silicon, right? How much it reduces the time and development effort, right? Because we don't necessarily have to worry about hardware, mechanical capabilities, right? And it can potentially streamline and make the communication a lot faster. We understood the different components of the OpenAmp framework to allow multiple cores on the same silicon to communicate with one another. We learned about Remoteproc, we learned about RPMsg, and we learned about the support for the Toradex Verdin i.MX 95 in Zephyr, right? We compiled a simple Hello World application. We loaded it from Linux to the M7 on the Verdin i.MX 95, and then we finally compiled a more complicated example. We wanted to see communication between the Linux A core and the ARM A core running Zephyr on the i.MX 95, and we not only loaded it, which the process was the same as the Hello World, but we also saw communication between Linux and Zephyr. And so some of the next steps that I think would be cool is creating like an actual real example using the OpenAmp framework on this particular platform. It's pretty powerful, right? It can enable a whole slew of new applications. With its NPU, you can do some really cool machine learning applications, and then use it to control, a robot, or use it to control like a medical device or an automotive, right? Where you can tell commands or get feedback from the ARM M core that's present and do some more real-time operations. And we can also design a more sophisticated protocol for communicating between the Linux and the Zephyr side as well. So I believe that's it. So I think we're going to transition now to the Q&A session.
Yeah, that's great. Thank you, Mohammed. That was very, very interesting. I will make one comment. You mentioned the idea of controlling a robot or something. If you've seen any of our recent embedded world demos, we do have our two-wheeled robots that are self-balancing. They're not running Zephyr. At the moment, they're just running some bare metal code, but it uses a lot of these similar techniques for communicating between the domains. So it definitely can be done, and I know we've talked about maybe trying to port that code over to Zephyr, so that'll be an interesting follow-up. Okay, so we got a couple questions coming in here. What the first one? What's the upstream status of the Verdin i.MX 95 BBK?
So this is it is so what I showed is, although it's a fork of mine, I just synced it to the upstream, so it's there. Like you can do that today.
Oh, okay. And what about it? I guess I know when I played with this stuff in the past, getting it merged and getting documentation and getting it listed on the supported docs page, is that an additional effort beyond what you've done?
So just to be clear, like what I showed today is nothing that I've written code for or upstream. Like it's already there. So like the
Oh,
documentation,
okay, gotcha.
it's part of mainline Zephyr already, like support for the 95.
Gotcha. Interesting. Okay. What about functional safety standards? Does Zephyr comply with any of those? Any, similar to, I guess, Safe RTOS? Are you familiar with any of that?
Yeah, so there's a big push right now. I think getting Zephyr certified is the next big kind of overarching goal for the group, and I think they're almost there. There's a lot of work done in the past couple of years to overcome a lot of the documentation hurdles that they've worked with a fair number of automotive companies to bring them on as partners, and other sort of functional safety kind of umbrella organizations to get them through that process. So it's underway, and I think it's pretty close. It's imminent.
All right, very good. What about, are there any other RTOSs that are supported on the Toradex hardware? I guess that's more a question for me. I know that in the past we have had support for free RTOS, and there's a lot of community ports of various RTOSs. In a lot of cases, they may not directly support, say, the actual Toradex module, but you can configure them for the generic M4, M7, whatever is on the SoC. So there should be, if you have another RTOS that you particularly like, it should be possible to get it up and running. You might have to jump through some hoops as far as disabling things in the Linux device tree to make sure they don't conflict and that kind of thing, but definitely should be doable. I don't know, Mohammed, have you had any experience with anything beyond Zephyr on Toradex hardware?
No, not really.
Okay. All right. Any decisive arguments for Zephyr versus free RTOS, or is it more of a personal preference, i.MX versus VI kind of issue?
So I know in the past that Zephyr has lagged in terms of like pure performance numbers with free RTOS. But that gap is, I think, closing, and that's kind of like one of the advantages of Zephyr. It's like, we noticed a problem, right? We started running like ThreadX's benchmarking, right? It's generally used as a golden standard for benchmarking like any sort of RTOS. And so when we did that, we noticed that it was clearly lagging, right? So when we let the when kind of the maintainers were aware of that, right? It's like, okay, well, let's pull in that framework, right? Because we had to cobble that together. So it got pulled into the latest 4.1 release, and they understood, like, okay, these are the improvements that we need to make. And so it went ahead and it made it, right? And so the fact that, okay, there's a group that is vendor neutral, right? Some of the problems that I have with other RTOSs is you may be tied to a particular vendor. And so Zephyr is essentially vendor neutral. And it's open source, so you can push up PRs if you see a problem, and the community is kind of open to just accommodating, right? Accommodating if you have real technical feedback, you can have somebody listen to you. The other big thing that for me, and I think it's useful for a lot of newcomers getting in, is that kind of going to my original point is it's not just an RTOS, it's an ecosystem, right? So if I need to figure out, like, okay, I want to do BLE, or I want to do like cellular, or I want to do some other sort of like co-app, right, for IoT, what source code do I use, what stack, right? So in my experience in other RTOSs, that's not always a clear answer, and going through the process of making that determination is not trivial. Like, I need to spend days or maybe even weeks trying to vet out different code bases that I see to like, hey, does it meet my requirements? Where
Right.
that's pretty straightforward with Zephyr, right? And if it doesn't meet your requirements, like, okay, at least you have a starting point and you can start making changes to something that somebody already that's a lot smarter than I am has vetted, and okay, I can take what they've given me and start building off of that instead of like, oh, I have to like start from scratch essentially. So, to me, it's a lower barrier to entry, and it's I want to write application code. I want to deliver a product, right, for my clients. I don't want to have to worry about the weeds about, oh, which is the right stack to use. So it just helps me get going a lot faster.
Oh, nice. Very good. All right. Well, I think that's it. We're about out of time. I just want to say thank you to everybody for your time and attention. We know how valuable it is. Hopefully this was useful. The video will be made available in about a week. And I know, Mohammed, you said you were going to follow up with a blog post with more details and links to other materials and things that you've generated. So with that, Mohammed, I'll give you the last word.
Yeah. Thanks to Toradex. They're always a great partner, and Drew and has always been awesome hosting webinars together, and I hope everybody has found this useful, and I'm excited to see the applications that everybody develops on Zephyr, on multi-core HMP sorts of platforms, right? It'll be pretty cool to see what's coming out. So yeah, thank you everybody.